Now, all these signals, as I mentioned, are those which are smooth, which are continuous by themselves, also have continuous derivatives. There is a need to have a compact notation for signals which are discontinuous, which are either discontinuous or have discontinuous derivatives. Take for example this particular function. Of time, or for that matter another one like this. Suppose these are the two functions of time that are given to you. F2 and t. It is difficult to describe this analytically because we have to say that function is 0 for negative values of time, and from this point to this point it has got certain, you give an analytical expression for this, from this point to this point you give another analytical expression for this, and beyond that once again you say it to 0. Similarly, if you want to describe this f of 2 analytically, you have to say it is 0 for negative values of time, it is a constant up to for t in this range, another constant for t in this range, and it has got a certain straight line relation in this range, and beyond that it is 0. That means you have to describe, give separate expressions for 5 different regions as far as this function f2 is concerned. So it becomes a little cumbersome, but one would like to see if we can express this by means of some notational expressions, some notations, just like as we have said this is a e to the power of st. Is it possible for us to arrive at some kind of expression for these signals f1 and f2 where we do not have to qualify them further as saying this is valid for this interval of time and this expression is valid for a different interval of time. And this leads us to the topic of what is called singularity functions, which are used to describe functions of this type, which are discontinuous by themselves or have discontinuous derivatives. And it is the singularity functions which we will take up for discussion later. And one of the most important singularity functions is the unit step function, which I will describe in a moment. This is originally introduced into the literature by Oliver Heaviside, a British engineer who made signal contributions to communication theory and operational methods of analysis of networks and systems. He was a controversial figure, and most of his work was not founded on rigorous mathematics. So he got into trouble with mathematicians of his day, but he introduced the step function among other things and the operational calculus methods, and as a retort to the mathematicians who were not happy with his work, he would say, do I stop eating because I do not exactly understand the process of digestion. That was his retort to those people who were critical of his work, because he introduced some methods and they were working, and so he said, why should you probe further into this? As long as it produces results, you should be happy with them. That is just a brief historical note on Oliver Heaviside, who introduced the unit step function, which we will take up now. We shall now take a look at 3 important singularity functions. These are called singularity functions because either they have discontinuities or the derivatives have discontinuities, and therefore in the regular classical sense of mathematics they do not have derivatives. If derivative fails to be continuous, in classical mathematics you say it does not have a derivative. So it is singular at that point. I mean, that is why these are called singularity functions. The most important perhaps is the unit step function, and this is what I said was introduced by Oliver Heaviside. This is indicated as u of t, symbolically it is represented as u of t, and this is defined as 1 for t greater than 0 and 0 for t less than 0. So, the waveform for this would be, it is 0 up to this point t, this time axis t 0, and then from this point onwards it has a value 1. So, as a function of time it has got a waveform like this, 0 for negative values of t and a constant 1 for positive values of t. At t equals 0 itself, at this point we do not really care what it is, it can be left undefined. You can take it as 1 if you wish, 0 as if you like, or half, whatever it is. Normally we were not really concerned in most of the work, it does not matter how you take it. So, we leave it undefined, but if really it becomes necessary, you take it as half, because it is the average of the right and left extreme limits, and in some limiting process it will converge to that value half. So, you may take it as half, but in any case the important thing here is that it is a discontinuous function of time. It is the left hand limit is 0, and then suddenly it jumps by a value 1 and stays constant from that point onwards. So, it resembles a step here at this point, a steep rise, and that is why it is called a step function, and since the height of the step is 1, it is called a unit step function u of t. Now, using this unit step function we can describe a number of other functions of time which have discontinuities. So, let us take a series of examples to illustrate how the unit step function can be used to describe different types of functions. Suppose I have a function which has got 4 units for positive t and 0 for negative values of time, then obviously this will be described as 4 times ut, because it is the same unit step function enlarged 4 times. So, the amplitude is 4 ut is this function. Suppose I have a step function which starts at t equals 2 and 0 for negative values, for values of t less than 2, then you would and the magnitude of this is suppose 1, then you would call that u of t minus 2, because as long as the argument t minus 2 is positive, t greater than 2, it has 1. If t is less than 2, u of t minus 2 is a unit function unit step function of the argument negative values, then therefore it becomes 0. So, this describes this function is described by u t minus 2. You can also see if this is u of t, it is translated in time delayed by 2 seconds. Therefore, if this is f of t, this must be f of t minus 2. Therefore, from that argument also you can see that this is u of t minus 2. Suppose I have a function like this, 1 for t less than 2 and 0 for t greater than 2. So, what will you describe this function as? Now, this function has a value 1 as long as t is less than 2. Therefore, if you write u of 2 minus t, that describes this function, because as long as t is less than 2, 2 minus t is a positive number, and therefore it must have a value 1, and as long as t exceeds 2, 2 minus t is a negative value, therefore it becomes 0. That is how it goes. Let me now take a case where you have a function whose value is minus 4 for t less than 2. Therefore, this is u of t minus t, but instead of having plus 1, it has a value minus 4. Therefore, this will be minus 4 u of 2 minus t. That is how it is described. You can substitute different values of t and see that it is in accordance with the definition of the unit step function. unit step function is also useful in describing functions like this. This is a kind of pulse, sometimes called a gate function, because it is like a gate between this interval. The signal is there, afterwards the signal is not there at all. Now, such functions can be easily shown to be the sum of two functions. For example, if I have a step function starting at 2, say f1, and another function f2 starting at 3, notice that if I subtract f2 from f1, from t equals 3 onwards, this area is cancelled out by this area, and what is left is only the value of the function between 2 and 3, and that is exactly what we are having. So, a gate function or a pulse function can like this can be written as u of t minus 2. U of t minus 2 would be a step starting at 2 seconds and going on forever. You want to pull down that step to 0, therefore, at this point 3 you have to introduce a negative step of unit magnitude, so that the original step that was going like this, from that you are subtracting a negative step, so that from point t equals 3 onwards it becomes 0. So, you need to subtract from this u of t minus 3. So, you can see that a pulse like this can be described in terms of step functions as u of t minus 2 minus u of t minus 3. So, this is a very useful concept which we can use to describe discontinuous functions of this type. Another example, suppose you have this function which is symmetrically situated around the origin, then you can think of this as a step function starting at this point, and subtract from that a step function a negative step starting at this point. The step function starting at minus 2 has 4 units, therefore, 4 u of t plus 2 you must write, because for t less than minus 2, then t plus 2 is negative, therefore, this is 0. As long as t is greater than minus 2 or t plus 2 is positive, you have a value 4. Therefore, 4 u of t plus 2 is a step which is going like this. But then you do not want this step to continue forever. At this point plus 2, you want to introduce a negative step of 4 units, so that this portion is cancelled by this. So, from this you subtract minus 4 u of t minus 2. So, the sum of these two is indeed this pulse that we are having. A little more complicated situation. So, suppose this is 1, this is 2, this is minus 1 time 2, 3, this is t. So, this goes on like that forever. Beyond t equals 3, this continues at minus 1. So, to describe this, always what you should do is you should start with the first step and see what are the other steps that you have to be added to that in order to describe the actual situation. So, this function is 0 up to this point, and at that point it jumps by value 1. So, you can write this as u of t minus 1, that describes a unit step starting at t equals 1 and going on like that. And that explains satisfactorily the given function of time from t equals minus infinity on up to 2. This function describes the behavior at this point. At this point, the function jumps up by another amount equal to 1. So, to this step you have to add another step of unit amplitude. So, that will be another unit step starting at t equals 2. So, u of t minus 2. And now, what is the effect of these two steps? you have 0 up to this point, 1, and then it continues like that. So, the effect of these two would lead to us, would give us a curve which goes like this and then continues like this. But then what happens at t equals 3, you must bring this down to minus 1. So, you must introduce a negative step of 3 units in order to pull this value down to minus 1. So, minus of 3 u of t minus 3. If you do that, then this value is pulled down to minus 1, and then from that point onwards it continues at a constant value. You can verify the result. After all, u of t equals 1 for t greater than 0. Therefore, suppose you take a large value of t, say 6 or 7, then this is 1, this is 1, and this is minus 3. So, 1 plus 1 minus 3 is minus 1. So, indeed that is minus 1. So, for any value of t greater than 3, this is going to be minus 1. So, these examples are to illustrate the usefulness of the step function in describing discontinuous functions and are piecewise constant functions, and you must get the facility, must develop the facility of describing such functions by means of appropriate steps with appropriate weights and appropriate shifts in time, as we have indicated by means of these examples. The next singularity function that we would like to talk about is what is called the unit ramp function. This is also a causal signal like the u of t, in that it is 0 for negative values of time. It is indicated as RT, and it is defined as t for t greater than or equal to 0 and 0 for t less than 0. So, it is clear that its waveform would be like this, it goes on like this, and it has a value 1 when time t equals 1. So, it is for positive t it is described as t, and for negative values it is 0. So, this is called a ramp function because this is like a ramp, a slope. So, it is called a ramp function, and since the slope is equal to 1, it is called a unit ramp function. The slope of this, suppose I indicate the slope by brackets, this is slope equal to 1, it rises by unit amount and unit time, this is called the unit ramp function. Now, unit ramp function, once again let me illustrate its applications through examples, see how we can describe several interesting wave shapes through the unit ramp function. Suppose I have a function like this which is 0 for t less than 1 and increases at the rate of 1 unit per unit distance travelled along the x axis, then this would be called r of t minus 1, because it is the same unit ramp function shifted in time, delayed in time by 1 second, and therefore this will be r t minus 1. We should be able to recognize whenever a function is delayed by an amount tau, then f of t becomes f of t minus tau. Suppose it starts at 1 and is a negative going ramp, at 2 it is equal to minus 1, then it will be minus of r of t minus 1. It is a ramp function with a coefficient of minus 1 and it starts at t equals 1. That is how you describe it. Suppose I have a function which is 0 for positive for values of t beyond 3 in the positive direction, and then it increases in the negative direction of t with a slope equal to 3, or slope in the as t increases is minus 3. Then first of all it is the ramp function has values for t less than 3, therefore you must have basically something like r3 minus t, because when t exceeds 3 this becomes 0. When t exceeds 3, 3 minus t is a negative number and therefore this is 0. So basically you have r of 3 minus t. Now you must fix the coefficient to suit this. Now when t equals 0 for example, then this is equal to 9, the slope is 3, therefore if you put here 3 rt minus 3, this becomes answers this description, because all you have to do is you must ensure that this is negative for t greater than 3, and therefore the break point comes at t equals 3, and beyond that if you fix one point on the straight line, the straight line gets fixed up. Therefore when t equals 0, this is r of 3, r of t is equal to t, r of 3 is equal to 3, therefore 3 times 3 is 9, and that answers this particular description. So that's how one can fix up this. You can do it in different ways, but at least this is one argument to show that f of t is equal to 3r3 minus t. As a fourth example, suppose I have a triangular wave shape 1 minus 1 4. This is a function which you can decompose as, first of all, at t equals minus 1 there is a step, there is a ramp function going up like this at t equals minus 1. So if a ramp starts at minus 1 and increases with a slope of 4, then you would describe this as 4 r t plus 1, because this is delayed, this is advanced in time by 1 unit, therefore r of t plus 1. So such a line, that is a line starting from here and then going on like this, would be called 4 r t plus 1. All right. Now if this is the line that is going, then this describes a waveform which is going like this. But now at this point at t equals 0, you must pull this down so that it will have a slope of minus 4 from that point onwards. Therefore in order to pull this down to introduce a resultant slope of minus 4, this has a slope of plus 4. At this point you must introduce a negative going ramp to pull down the slope to minus 4. So at this point you must introduce here another ramp with a slope of minus 8 units. This has a slope of plus 4 units. This must have a slope of minus 8 units, and this ramp is introduced at t equals 0. Therefore this will be called minus 8 r of t. That will be that particular characteristic which starts at t equals 0 and has a negative slope. Now what is the result of these two? If you have these two together, then you load out this increases. At this point you pull this down and then it's going on like this. Now at t equals 1, we must arrest this downward slope. We must put this back to 0. That means this slope, resultant slope of minus 4 must be stopped, and then it must be restored to a DC 0 slope. Therefore at t equals 1, you must introduce another ramp with a positive slope of 4 units, so that that particular ramp and this what you had earlier picked up will lead to a 0 identically for values of t beyond 1, and therefore this would be called 4 r of, this ramp is introduced at t equals 1, therefore 4 r t minus 1. So ultimately this particular, and if you do that, then this resultant negative slope and then this positive slope will be cancelled out, and yielding identically a 0 value for t equals 1 onwards. Therefore this particular triangular waveform can be described as 4r t plus 1 minus 8r t plus 4r t minus 1, the sum of these three. That is how this ramp function can be employed. Notice that RT is not equal to T, they are not the same. RT is a function like this, whereas T is a function like this. This is RT, this is T. T has a value for negative values of time as well, whereas RT is 0 for negative values of time. You can however say RT equals T times ut, you can say that, because if you take this T and multiply by unit step function, the negative values will be multiplied by 0, it gets cancelled out, and for positive T, the T multiplied by 1, T ut will provide RT. So RT can be written alternatively if you wish as T ut, but it can't be equal to T by itself.